All right, this is Unit 6C in Math 1030, looking at the normal distribution. And so when we look down below here, we have two examples of what is often referred to or called a bell-shaped curve, but it's more frequently known as the normal distribution. And this normal distribution arises so frequently that we do give it pretty close attention in statistics. And the normal distribution, it looks, we call it bell curve because it tends to look like a bell. And it's got one peak, and that peak can either be really steep or more spread out depending on the size of the standard deviation. So if your standard deviation is small, you're going to get a higher peak. If it's larger, it's going to spread out that data more. It's going to bring that peak down. And when we look at a normal distribution, it can be characterized by just two numbers, the mean and the standard deviation. So the mean determines the peak, or the location of the peak, and the standard deviation describes the width. So again, notice in this example here, they both have a mean of 75, but one is much taller than the other. And since they are bell curve, they are both symmetric as well, which will be really helpful in doing some of the calculations. So there's your general definition. Normal distribution is a symmetric bell-shaped distribution, single peak. The peak does correspond to the mean, median, and mode of the distribution, and the variation is characterized by that standard deviation. So what type of things follow a normal distribution? So in order to better appreciate the importance of the normal distribution, it is good to understand why it's so common. So let's think about some human characteristics. One example would be height. Most men and women have heights that are clustered near this mean height, depending on the sex, male or female. And so the data of heights has a peak at a mean height. But then as we consider heights that are increasing far from the mean or decreasing, so on either side of that mean, we find fewer and fewer people. This is what we call kind of tailing off in heights, and it produces two what we call symmetric tails on either side of the mean. So when we draw a bell curve, these are going to be what we call the tails here on the outside. That's a terrible bell curve, but it just means we get fewer and fewer data points as we get farther and farther away from the mean on both sides. And if you think about height, you have people who are kind of right in the average or mean area, and then you have those who are a little bit more abnormal as far as they're much taller, and there are not very many people who have extreme heights or extremely short. So the bulk of people lie kind of in the middle of the data here. And so, when we look overall at this, then, for human height, the distribution closely approximates this normal distribution. Now, if we look on a deeper level, any quantity that results in many factors, so, height has a lot of factors in there, is likely to follow a normal distribution. So height is the result of a lot of genetic and environmental factors, genes, diet, and other things and there's a lot of genes in a person, so there's a lot of different factors that go into it. Another example is scores on SAT or IQ test. They tend to be normal because each test score is determined by many individual test questions. So again, when there's a lot of factors going on, we have a tendency to see normal distribution. Even sports statistics such as batting averages in baseball tend to be normally distributed because there's so many people involved with so many different levels of skill. And so we would expect a data set to have a nearly normal distribution if it follows the following or meets the following criteria. Okay, 1, most data values are clustered near the mean, giving the distribution a well-defined peak. So you've got to have a mean where the majority of the data is around that mean. Okay, and then the data values need to be mostly, but spread evenly around the mean, making it symmetric. And then the larger the deviation from the mean, the more increasingly rare it becomes. So this produces those symmetric tapering tails that I mentioned before. And then last, what we just barely talked about, individual data values result from a combination of many different factors, such as genetic, environmental factors, as one example. And there are more complex ways to go about this, but for us, this will suffice. So let's look to see a couple examples here if we feel these are normally distributed or not, and why we think they are. So if we look, number 13 says the delay in departure of trains from a station, and then note that trains, buses, airplanes, and so forth can't leave early. They're not supposed to leave early. Get people who are quite angry. So if you look at this distribution of the delay times, we would expect that the majority of these departures we'd expect the majority of the trains to depart on time or close to on time, so the majority have a small delay, but they're not going to have negative delays. And so if we're expecting a small delay, then we would see a peak early on and then a taper off where you get those really extreme late leaving. So this would be more of a right skewed type of distribution rather than a normal, because we can't have negatives on those delay times, because zero delay time means it left on time, negative means it left early, and again, leaving early would be frowned upon if you were a passenger who got there right on time and they already left you. So this would not be normal when we look at that. The next one, the weight of bags of flour labeled 25 pounds. And now if you think about label or bags at 25 pounds, say here's our 25 pounds, and you would expect that if you looked at the data, that the majority of that data, so say this is, and they're probably very precise in their measurements, so like maybe this is like 24.8, I'm just making up some numbers here. Maybe we're like 0.2 above and below the mean. You would expect that the majority of the data is going to be somewhere really close to the mean, with very few extremes out here in the tails. But you would expect the majority to be right on par with 25 or within a couple tenths of a pound. And so that would be normally distributed, because some of them might be a little teeny low, some may be a little bit big, but again, the majority are going to be right close to that 25 pounds, and you have quality control that they use to try and ensure that. But this would definitely fit a normal distribution, so we'd say normal on that. It doesn't look like normal, but that does say normal. So that's, and again, we're just trying to explain our way through. We don't have data. We're just making some assumptions here, trying to make some educated guesses based off of those assumptions. Now, when we look at the standard deviation and normal distribution, again, this tells us how spread out our data is. Okay, now, again, they all follow, all our normal distributions have kind of the same or similar bell shape. When we know the mean and standard deviation of the distribution, it tells us a lot about where the data values actually lie within this thing. So again, if we recall from Unit 6B, the standard deviation gives a measure of the average spread of data values around the mean. And there's a simple rule. It's often called the 68, 95, 99.7 rule, sometimes referred to as Empirical Rule, that gives some approximate guidelines. So these aren't exact, but they're pretty close. But it gives some approximate guidelines for the percentages of data that lie within 1, 2, and 3 standard deviations as the mean for any normal distribution. And here's kind of how this works. So there's a lot of information going on there, but if we go 1 standard deviation below and 1 standard deviation above the mean, then this area underneath the bell curve will include 68% of our data. So another way of thinking of that is the probability that something is between 1 standard deviation above the mean and 1 standard deviation below the mean is 68%. So that's where the 68 comes from. Now if we step outside of that realm and we go 2 standard deviations out, so hopefully you can see along that x-axis there's 2 standard deviations and then -2 standard deviation. That just means above and below. If we go 2 standard deviations out, notice 95%. So if we were to think of this as area under the curve, 95% of the data is going to fall within 2 standard deviations above and below the mean. Okay, so there's going to be 95% there. So almost all of our data is 2 standard deviations, with the exception of about 5%. And then if you jump out, if you jump out 3 standard deviations, you get way out into the tails, like minuscule. That tells us that 99.7% of our data will fall within 3 standard deviations above and below the mean. So almost all of it, 0.03%, won't fall. They'll be beyond 3 standard deviations above or below the mean, but almost all of our data is 3 standard deviations above and below the mean. So once we know an average and a standard deviation, we're able to figure out how far these things are spread out, and kind of the likelihood. If someone says this is the mean, this is a standard deviation, and this is a data point, how likely is it that this is this data point will occur? We can get an idea based off of this 68, 95, 99.7 rule. But remember, the 68, 95, 99.7 applies to normal distributions, and we're looking at standard deviations either above the mean or below the mean. So when you see that negative on -3 SD, that just means 3 standard deviations below the mean. Okay, so there's the empirical rule, the 68, 99, 95, 99.7. So it says about 68, there's your exact number. About 95, there's your exact number. But about 68%, or just over 2/3 of the data points, will be within 1 standard deviation of the mean. 95% of the data will fall within 2, and then 99.7% of the data will fall within 3 standard deviations of that mean. So it's a quick way for us to determine, based off of those 2 pieces of information, the mean and the standard deviation, how close or how much of the data is contained within an area. So we're going to look at this example number 20. Let me check my time. So I'm going to run out of time here, but in this next video we're going to check out number 20 here and look at resting heart rates that are normally distributed with 70 as a mean and a 15 units for standard deviation, and we're going to try and find out the percentages that fall in these categories. So that'll be in part 2.